After those many talks on fitting many data sets at the same time, this is really something simpler. It's the HERA analysis. And we found in our analysis of PDF fitting analysis of HERA inclusive DIS data that we really couldn't get a good handle on alpha S, trying to determine that on the PDFs at the same time from the main fit to inclusive data, because the correlation of the gluon shape to alpha S itself is so strong. So we added our own DIS inclusive jet data, well, in fact, jet data and dijet data to give us another handle on this. And I think I'm talking to a sufficiently educated audience that I don't need to show you Feynman diagrams about why it is that measuring jets will give you an alternative handle on the gluon and hence help you to weaken that correlation. In fact, we did an analysis of this at next to leading order when we presented the final HERA combined data in 2015. But at that time, this was the one part of the analysis that we couldn't, in fact, take up to next to leading order because there were no such predictions for the jets in deep inelastic scattering. And now there are. And in fact, it's been a bit of a long road. We thought that we had these predictions from the NNLO jet group back in 2020, but it turned out that there had been a bug. And so finally, the correct grids for doing your jet predictions were not available to us till 2021. And we've implemented them as predictions with the AppleFast grid system to do this analysis. It's a simultaneous PDF and alpha S fit analysis, not just an analysis with fixed PDFs. And as well as the value of alpha S itself, we issue 2 new HERA PDFs at the alpha S value of 118, the PDG value, and at 1155, because we found that our determination of alpha S at NNLO was significantly lower than what we had got at NLO. And I've given the bottom line on the bottom of the slide, but in view of the many discussions that have been going on here, I should say that the largest uncertainty on this determination is the last one, the 0029, and it is the theoretical uncertainty. It's the scale uncertainty on the jets. So it obviously relates very much to the, the fact that we need to know more about the missing higher order corrections. Anyway, let us proceed right now. The HERA PDF approach uses only the HERA data. From that combination of HERA data, we have a very accurate and consistent data set for the E+ and E- neutral and charge current reactions. And we also have this at several different beam energies. So effectively, the measurement of FL, which changes as the relative importance of which changes as the beam energies do, is built into this. And the fact that you have charge current gives you valence information, and the fact that you have a difference between E+ and E- at high scales also gives you valence information. So it's a single consistent data set to try and determine PDFs on which we can use the conventional delta chi² = 1 criterion, because it's at least consistent with itself. Note it uses a pure proton target, so you don't need to make deuterium corrections, which is perhaps the only disadvantage of using deuterium, because there was some concentration on what a nice idea it is to have a deuterium target earlier in the session. The D-valence itself is extracted from the charge current E + P events. Okay. And sorry, I can hear some. Is everybody muted? Okay, carrying on. The D-valence is unusually extracted from the charge current E + P. You don't need to assume strong isospin, D in proton is U in neutron, and vice versa to get at that. And all the data are at high W, so you don't suffer from the kind of low Q² higher twist effects that occur at high X, because simply when you're at low q squared and you're not at high x at the same time in HERA. So that's one thing you don't have to worry about. The HERA PDF also evaluates some of the uncertainties on the PDF and alpha S due to choices of various model parameters and parameterization. And obviously it's based on the latest combination of HERA 1 and HERA 2 data. So the HERA 2 jet fit adds our inclusive jet and dijet data to this. I think I've gone too fast there. Actually, I'm trying to find where I've listed. Right, okay. Right, the jet data sets that are used in the NNLO analysis are given on this slide. They're largely what was already used for the next to leading order analysis, but there have been some new data sets added. H1 brought out both inclusive and dijet data at low q squared, and it being at low q squared means it obviously has somewhat more sensitivity to alpha S. And those have been added to our previous jet data sets, but it also has been necessary to subtract some data sets from the NLO analysis. There are still no predictions for trijet, so those are not used. It's also true that if you want to get a decent result out of this, you can't go to too low a scale. So we have cut data at a scale, the combination of sorry, there should be a square root in there, square root pt squared plus q squared less than 10 GeV. If you go lower than that, the scale variations do start getting very large, and hence we've tried to just confine ourselves to a kinematic region where they're smaller. And it's also true that we chose rather non-optimal cuts for the Zeus dijets, and that means that our points at low PT are not really truly predicted at NNLO. So we've also cut out 6 low PT points from the Zeus dijet sample. Okay, already went through that. So I'd already mentioned the philosophy of the HERA PDF. This is just a specification of the parameterization, which anyone who's read the HERA PDF knows about, but there are the usual, there are 14 total free parameters in that. There are constraints on the normalizations from the quark number sum rules and momentum sum rule. There has to be some constraint on how much of the D-type PDF you think comes from the strangeness, because HERA itself cannot determine that. And we determine the parameterization by the usual procedure of starting with a minimal number of these ax to the b1 minus x to the c parameters and adding extra parameters until the chi-squared no longer improves. Having got to that point, it's still the case that even without a chi-squared improvement, you can sometimes get a change in shape. And so we persist a little bit further than where the chi-squared is saturated, and we look at parameterization variations from adding a small number of extra parameters, which slightly change PDF shape. Okay, so the specifications of it for the model choices are given here, right? We usually cut all data below q squared of 3.5, but we have a variation upwards and downwards on that to check sensitivity. Our assumptions about the fraction of strangeness are also chosen to vary from, in fact, the maximal when it, strange would be equal to D type, and the minimum when it would be more like a half. We also vary the charm and the beauty mass, which is input to the formalism, from central values which we determine ourselves, and I'm just about to show that, and a downward and upward variation. Unfortunately, since we're going to generate all our charm perturbatively, we have to require that the starting scale for evolution for our fit is less than the charm mass, and hence you can't make some of the downward and upward variations of mass charm and the starting scale at the same time as each other. So we make the ones you can make and symmetrize in the other direction. And then finally, we also vary that starting scale for the evolution from 1.9 down to 1.6 and up to 2.2, as well as looking at this additional parameters in the fit. So since the publication of HERA PDF 2.0, there's been another new thing on the HERA front, which is the new HERA combined charm and beauty data. And that affects to some extent our evaluation of what the optimal values would be for the charm and beauty masses for our fit. For the inclusive DIS data, the heavy quarks are dealt with through the Thorne-Roberts optimized variable flavor number scheme. And we can actually perform chi-squared scans against the choice of the pole mass of mass charm and mass beauty by adding our combined charm and beauty data to the inclusive data to see what the sensitivity to that is. And these are the scans that you see on this page, determining the optimal value for this as a parameter and its allowed variations. I'm not going to read out what's there on the entire slide, but essentially it's an iterative process, because you start with a certain assumed value of alpha S and you check out what would be the charm and beauty masses, but then if you then do a fit for alpha S, you find it's different. So you have to go back and check that it's okay again. And then you have to check that it's okay with your parameterization again, and so on. So we iterate around until there are no further changes, basically. Then there are certain choices you have to make when you're putting in the jets. The jets themselves, of course, are at much higher scale. They're dealt with by zero mass variable flavor number schemes. And they also, you have to make a choice of the scale for the jets. You have to make hadronization corrections on jets. So first of all, the factorization scale is now chosen as Q squared plus PT squared for all the jets. This is a slight change from our previous analysis, because really choosing a Q squared is not a good scale choice for low Q squared jets themselves, where the PT is larger than, PT squared is larger than Q squared. The renormalization scale, again, we've chosen this time as Q squared plus PT squared, when previously we had chosen that divided by a factor of 2. The reason for the new choice is that this is the better choice from the point of view of Q squared. And it is, in fact, just to note that the choice of the optimal scale is different between our NLO and NNLO analyses. We will also, of course, explore the consequence of scale variation. And then finally, if you've got jets in your data, they are subject to hadronization corrections. These are included along with all the rest of the experimental uncertainties, treated as 50% correlated and 50% uncorrelated between the bins. And another small uncertainty we have is that the theoretical predictions themselves that we have, right, also have a slight statistical uncertainty component. You really have to run these things for a very long time to eliminate that altogether. And so that has also been added in, 50% correlated and 50% uncorrelated. Okay, so what do we get, right? We do a fit simultaneously with the PDFs for alpha S and the results written on the bottom of the page. But what we also do in checking it out is that we do fits for fixed values of alpha S, changing that value of alpha S in very small steps. And you see that parabola there on the plot. So you can see the chi-squared parabola for the value of alpha S, which coincides very nicely with what we get from the free fit. You can also see on that the experimental uncertainties from this fit, taking into account the hadronization uncertainties and so on in the red band. Then that's slightly augmented in the green band to account for the model and parameterization uncertainties, which it turns out add very little to this, which is why you can hardly see it. And then finally, the size of the scale uncertainty is illustrated on this plot as well. So, as I just said, in fits with free alpha S, the scale uncertainty becomes important. We determine this from the usual procedure of varying the factorization and renormalization scales both separately and simultaneously by a factor of 2, and taking the maximum positive and negative deviations. We also do this with the usual 7-point procedure, where you don't allow the factorization scale to go to a half when when one of the other scales is going to ×2 at the same time. So it's the 7-point scale variation. And what it does is add this error plus or minus 0.0029. It's roughly symmetric to the overall uncertainties. So, if one of the questions we're being asked is what is really the sticking point in this determination, it is certainly whether or not that could be reduced. And indeed, is it reduced at N3LO? In the blue box at the bottom of the slide, I'm just comparing the chi-squared for the free alpha S fit, which is 1614 for 1348 degrees of freedom, to the chi-squared that you get for a fixed alpha S. You can see that there's just a marginal improvement between the fixed and the free, but it's significant nevertheless. And these kind of values of chi-squared for HERA around about 1.2 are typical. They're what everybody gets in fits to these data. Now, to just illustrate the power of the jets, we compare here that chi-squared scan I already showed to what you get when you do it for the inclusive data alone without the jets, which is shown on the bottom. So you can see just how much having the jets, tightens the shape of that parabola and gives you a decent determination. But what's also shown on these plots is that we varied that minimum Q-squared of the data from 3.5 up to 10 and up to 20. And you can see that once you have the jets in the fit, you don't get a big difference between those Q-squared cuts. It's probably a good idea to consider this as it's kind of part of the theoretical uncertainties, because the higher in Q-squared we go in HERA, the more of the low X data we're cutting out. And so we're getting away from the biases inherent in the possibility that you might need things like log1/x resummation to describe the really low X. Another thing that's mentioned on the bottom of the slide is that we chose a particular parameterization of the gluon with a negative term in it. And we've also tried removing that term and adding extra terms to the gluon to see how sensitive it is to that description. And as you can see from the values given there at the bottom, it's barely sensitive at all. It's a change from 1156 to 1151 in alpha S. Now, to compare this NNLO analysis back to the NLO one that's already published, so the NLO curves are the top two and those NNLO ones I just showed are the bottom two, you can see from that, if you just look down, that clearly the NNLO value is lower, but I would just caution that the published NLO value has been done with a different scale choice and with slightly different input jet data sets. So had we harmonized all of that, we would in fact have found that the difference was even greater rather than even less, that the NLO value stays around 1186 and the NNLO value becomes slightly smaller, because if we cut out the new H1 low Q-squared data to harmonize it with the previous analysis, we find that that actually slightly reduces the value. So this is a very real shift that we have between NLO and NNLO. And so if that's some measure of the, I would say it's larger actually than the current scale uncertainty, but it may give us some hope of progress for N3LO. Another comparison that's pertinent at this point is that in the previous NLO analysis, we also applied scale uncertainties, but we did it by a slightly different procedure. We actually had treated them not as fully correlated for the variations, but as half correlated and half uncorrelated. If we were to follow that procedure now on the new analysis, then instead of getting 0.0029, we'd get 0.0022. So if you compare our present NNLO analysis using that evaluation of scale variation to the published NLO one that you see below it on this page, you'll see that the scale uncertainties certainly have decreased quite significantly from NLO to NNLO. And that's good news. It gives us hope they will decrease yet more if we can ever manage to go to N3LO. Now, sort of to compare this result with using HERA jets to other results that have also used these. There was a study by H1 alone using just their inclusive data and just their jets. It used fixed PDFs, and the result is given there outlined in red. And what's mostly pertinent to compare is that they are scale uncertainties, at least are in the same ballpark, 0029 or 0038. And the values themselves, given the, the uncertainties on them, are similar. Just to note that those uncertainties called experimental hadronization PDF on the H1 analysis there would all be subsumed in our first uncertainty, since we're doing free PDFs, and we also have the hadronization included in that. But because that's a result for fixed PDFs, it's not actually, a completely apples for apples comparison. So that study also did make a free PDF analysis, which the result of which is given there outlined in black. This was done, however, for the harder cut, Q² greater than 10 on the inclusive and the jet data. So we repeated our analysis for alpha S using that cut, and we obtain the same central values and experimental values, but a scale uncertainty of 0021. So you can see that that agrees very nicely with the scale uncertainty evaluation of H1 alone. And the second result we might compare to is that the NNLO jet group, which provided the NNLO predictions, also made an analysis using fixed PDFs, using just inclusive jets from HERA, and that's their analysis towards the bottom of the page outlined in red. And we can see that if we compare our result to that, the scale uncertainties, ours of 0029 and theirs of 0033, are in nice broad agreement. That is really it for alpha S. So I'm just finishing up here by saying that, of course, the same analysis results in new PDFs, and I've put there a summary plot of U valence, D valence, gluon, and total C for the PDG value 0.118 and for the value 0.1155, which is suggested to us by our own NNLO alpha S fit. On the next page, you can also see those compared on top of each other, and you can appreciate that the only real difference there is in the gluon. On this page, we compare the new NNLO fit with jets to the one we published in 2015 without the jets at NNLO and using the same value of alpha S. And you can see that, in fact, the central values have barely shifted at all, but the uncertainties have improved. If we compare here the uncertainty on the gluon, the bottom right, in fact, is the change in the total uncertainties, and the rest of the plots are the same thing for subparts of the uncertainties. So top left is only experimental, top right is experimental plus model, bottom left is experimental plus parameterization, and as I just said, the bottom right is the total improvement, and you can see it has improved both, all over, but most of the improvement at low X is due to the reevaluation of the model uncertainties in the mass charm and the starting scale, whereas most of the improvement at high X is down to the jets. And since I am an experimentalist, I feel obliged to show one plot which shows you the quality of the in ratio of this fit in red to the actual some of the data sets that go into it in black. And then I come to my conclusions that we finally completed the HERA PDF family by doing the one thing we couldn't do before, a next to next leading order fit, including the jet data, which results in 2 new PDF sets and a value of alpha S at NNLO. If we want to compare that back historically to the NLO result we got, we have to use the same procedure for evaluating scale uncertainty, and that's the second line in red compared to the published NLO result in blue. And that's it. Thanks. That's all I've got to say.
Thank you very much for this very clear talk. Do we have questions to Mandy? Do you have questions here from the audience? Oh, let's see if... Yes, Simone, please.
So I have a very brief question, and maybe not super important, but about this issue of correlations, both about the theory scale variations and the some other uncertainties you mentioned. So if you go back to slide 7, actually.
Yes,
so
just a minute.
Sure. There, I think you discuss both the hadronization corrections and what I believe are just the integration uncertainties of the predictions.
Yes.
But what's the sense of taking them? So the latter, I think you should just take as uncorrelated, right? I mean, this is purely the result of a Monte Carlo integration, so it's completely uncorrelated beam by beam. And
if I can just interrupt there on that, this was the recommendation of the NNLO jet group themselves who produced these, so that there is something in their procedure whereby they think there are some correlations.
I see.
I can explain it if you want. So the predictions were produced with a very early version of NNLO jet, and this did not have the final combination procedure for combining all the thousands of different calculations that had to be run. And for the final results, one correction on the double virtual channel had to be implemented, but using a newer version with the final setup. And there are differences in the statistical combination from this very first preliminary version and the final version. And the half correlation takes into account that there's a correlation in terms of a systematic effect within these differences of the combinations. That is the reason. Otherwise, you're right, it would be a numerical independent uncertainty.
Thanks, I understand. I had in mind just a statistical uncertainty. While for the model dependence, and this is maybe not only relevant for this analysis, so these hadronization corrections, I guess one would actually want to maybe test different models for the hadronization corrections, but keeping them as 100% correlated rather than testing arbitrary correlation with a single model, no?
Yeah, in fact, I mean, some work was done on the correlations of the hadronization. In fact, it makes very little difference to the total result if we had done it completely correlated rather than 50-50. But it was decided that between, there clearly is some correlation between bins in something like that. But again, because it's being evaluated by looking at various Monte Carlos, there is also a statistical component in what you're doing. And this was just felt to be reasonable. But as I said, it actually is not a huge effect in terms of the final uncertainties on the analysis.
Yeah, thanks. And a super quick question then. So for the scale variations, you do them with the offset method, just to make sure I understand.
Yes, yes, okay. They are not, we do not try and evaluate numerical values for them and then put that as systematic uncertainties into the fit, not in this analysis. Right?
Okay, thanks.
Alexandra, you have a question?
Yes, thank you. So given that the scale uncertainty is largely dominant, have you looked into those scale setting procedure like the Brodsky, Lepage, Mackenzie, or its recent update, the principle of maximum conformality?
Okay,
because...
well, what I can tell you personally is that I have read these things and I don't feel I understand them sufficiently in order to be able to apply that. But it's certainly it's a good point to think about, given that this turns out to be the largest uncertainty in the analysis.
The claim from the author are that it basically makes the scale uncertainty negligible. And
I know, but well, I'm not sure how I would apply it to this jet analysis, I must say.
The issue is that then how do you assign an uncertainty if you do such a prescription? If you follow this prescription, what is then your uncertainty? This is the question, right? And if you can't, I don't think it should be used here, honestly.
Well,
because the main point is what is the scale uncertainty, right?
Well, there is still a scale uncertainty, but it's much reduced. And I have to say, I'm not an expert on that. I just
No, I think it's a good point to throw into the ring for people to think about, but I'm sorry, I can't really comment on it. I don't understand it enough.
Yeah, I think Alexandre, we discussed this with Brodsky in our previous meeting, and we don't understand it. I mean, what we know that there is a truncation of an infinite series of alpha S expansion, and we know that this introduces an uncertainty. So we need to evaluate these missing higher order terms. So the PMC approach does not tell you what is the size of these missing terms. So we tried to clarify this with Brodsky 3 years ago, as Julia was saying, and we couldn't find out
my understanding was that he agrees that he has no pragmatic procedure on assigning this missing higher order terms, on assigning the uncertainty due to that. And that's why I think at the end, I mean, besides other theoretical arguments, why it might not be advisable to absorb all the higher order terms in a scale choice when we know that there are higher order corrections that have nothing to do with that. So, but maybe we should now move on and maybe keep this as a point for our discussion session. Sorry. Unless there is another urgent question. Thank you, Mandigen. And we move then to the next speaker.
So I will speak about geopolitical scattering data with large-x-resummation. So it's really results done. It's a result done preliminary. So there is something calculated, something not. So the result done with together with Vasily Krivakishin and Binur Sheikhmadenov, and really it's based mostly for these two papers. Last two papers, but very old one. So next slide, please. For example, to study new physics methodology, if somebody studies necessary some threshold resummations of cross sections, for example, there is possible a lot of paper, but possible some paper of Benneke, Martin Benneke, and so maybe it's good to extract parton distribution function and coupling constant else from deep elastic scattering, but with resummation of large X. So if we consider structure function F2, but I will speak only of F2, so there is something like F2 contribution of F2 from perturbative QCD, so it's twist2 analysis, twist2 part and target mass corrections part, and there is some high twist corrections. There was a talk of Sven Moch, where all six was very good reviewed. So I will not do it so much. So please next page. So in principle possible to analyze in two way, possible to study mostly like people do study the GLAP equations and compare with data, possible to study structure function moments, which possible to do analytically and study with some experimental structure function moments. So it's quite difficult. We will do something between. So we study million moments, but reconstruct it, study square evolution of million moments, but always reconstruct structure functions using so-called Jacobi polynomial expansion method introduced by Parisi in Sorless in 1979, but some people from England and from Dubna participate too in these reconstructions. Please, next slide. So in principle, this structure function F2 contain non-singlet and singlet part, and possible to introduce parton distribution function on singlet gluon ones, and but because I will study large X regime, so to me we know gluons, so I will restrict we will restrict ourselves by non-singlet evolution. So please next line. So structure function moment structure functions relate with moments of parton distribution function. In this case, there is some normalization factor, and there is some so-called coefficient functions. So this complete constant like this. So next, please. So complete constant obey renormalization group equation in this form, and next line encoder and next line one. And there's an integral and there's a beta function. So next, please. So this is coefficient function. We will look only for first two terms, and for evolution of parton distribution function, we will have the same two terms. So this is leading code contribution. There is some two terms from next to leading one. So please. Next, so there's contributions coming from combinations of anomalous dimensions. So next slide, please. So it's possible to introduce some variation to study the property of perturbation series. It's possible to introduce some renormalization scale and factorization scale in this way. So this modifications will be modified this coefficient functions and the evolution of parton distribution function too. Please next slide. So the evolution, the modification is this form, and really often people use k equal 2 and 1/2, but next please. So, but we will do not study renormalization scale, but we'll study factorization scale. But we will study some n-dependent or x-dependent factorization scale. What's necessary? This is element dependent on normal dimensions, dependent only logarithm n. Anomal dimensions leading code next anomal dimensions at large n. Oh no please. So the dependent in simple form for large n, but the coefficient function strongly rise at large n. It's better to resum it. It's possible to do in several ways. For example, from some scheme invariant perturbation theory, there is a lot of people, a lot of papers, but we will use the Greenberg approach. Some DDS scheme. Before it was a lambda scheme, very old. In there something from W square evolution. So we will kind of replace Q squared by W squared evolution. So next, please. So now we consider this Greenberg effective charge method. So if we have some observable, we can this observable looks like new coupling constant, and this new coupling constant will obtain a result for some modification of Q squared. First coefficient will be modified argument, and another coefficient will be modified in new beta functions. So now moments have this form. But of course, we can transform so this variable to this one, like this one, for example, or using some logarithm. Fine, logarithm. So please next slide. So in principle, for this scheme invariant analysis, it's better to do normalizations for structure functions, Mellin moments, and this. Coefficient function, new coefficient function will take all Q squared dependence. And the normalizations, both normalizations through structure function and through parton distribution functions are related very similar, very simple form. So now we next slide. So now we can take this independent coefficients in argument of complement constant in this form. After this, we obtain so next leading coefficient 0. And the coefficient function will have this form. So next slide, please. And this new coupling constant will obey the renormalization group occasion like before, but with some additional factor. So it will be always equation 1. So next, please. For next leading analysis, we will have same. but same shift of argument, but we will have some new beta function which have this form. So after this, in next leading we will have both coefficient are0 but our coupling constant will be independent. So in principle, such analysis at next to leading is already done, very old. There is very old papers, but the main result, so alpha s is stable from this the transformation, and height is strongly decreased in this framework of this Hamming-invariant perturbation theory. We will confirm it later in our results. So now, please, next slide. So when we come to W square evolution, it's better to transform to X space because it's KF dependent on X space here. So the transformation is very same like before. All product of Milling moments are replaced by a convolution. It's all. So and there is some logarithm term and logarithm K square term. So next slide. So we introduce this form, and from this logarithm of this variation, we'll have some logarithm 1 minus x, logarithm x, and delta. All the terms come with logarithm x will be have index a, this index b, and this index c. Look, the next type, please. So after transformation, we will have A, B, and C at leading codec. Next to leading, we will have the same, but when there is logarithm square, it will be some more terms. So next slide, please. Okay, but next. So we really consider 4 cases. Firstly, we took only logarithm 1 over x. Second, logarithm 1x in logarithm x, and later introduce some constant. And like fourth case, we introduce mass proton versus W, it's effective mass diplastic scattering. So it will be looks like mass which come to froze coupling constant at low Q-square values. So next slide. So if we do analysis, for example, anomalous dimensions have this logarithm n analysis, logarithm n asymptotics at large n, B1 have logarithm square n asymptotics. So next slide. Next slide. So if we transform transformation only 1 over x, so we will have some additional contributions. And this additional contribution have logarithm square with another sign, and the combination will have only logarithm. So because most important terms are cancelled for large n. So next slide. So in its case too, when we add logarithm x, situation more or less same. So there is only logarithm n, and next slide. Next slide. So if we add this some constant, and we if we put special value of complex, we can cancel even logarithm n, right? So it will be some coefficient will be constant and go to infinity. So now, so and what? So in this case, we will have like a second case, but some proton mass will add in complete constant. So if we do the next leading analysis, the terms are very complicated. So we will look only term at large n. So we will call it like S. Is it what? So we will have this elements. This is leading code anomalous dimension next to leading coefficient. This proportional logarithm s squared. This s like before, and this proportional logarithm force. So if we please next slide. If we add this additional terms, next slide. Most important. Sorry. So most important term give us the same logarithm S force coefficient and with another sign, and the combination we will have only third power of logarithm n. Next slide. In the case two situation does not change, and the same the sum have only have a short power of s. And next slide. And in short two with the same delta, Next slide, please. With the same delta, like at leading coda, we will have only logarithm n square rise. So next, please. So if you look at the DIS scheme, we will have next to leading coefficient is 0, but next to leading vada it's non-zero, but most important terms are cancelled. In principle, why people told already it's possible to introduce some new scale at next to leading order to cancel this term too, but so it's like in principle of maximal conformity, but I will not do it here. So next, please. So now, so mathematical part is finished. Now it is fitting procedure. So we have a structure function. It's a reconstruct through Mellin moments. Mellin moments there are some evolution equations. Which Mellin moments can be solved exactly, and but reconstruction structure function can be reconstructed using these Jacobi polynomials, and it's with some maximal value of n, because Jacobi polynomial have same generation function. So in this case, function is reconstructed for very low value of n, less than 10. So next, please. File. So it's really at maximum it's 8. It's people study it. It's possible to use only first 8 moments. So experimental data, different experimental data, but like basic one introduce deuterium BC-based data, but another one has some small arbitrary coefficients around 1. So Q0 is always 19 GeV squared. And late, please. So unfortunately, for W evolution, we only considered next to leading analysis. So this is standard analysis. Look, this is chi-squared for this point, and alpha s have this result. It's coming from our previous analysis for previous paper. So when we introduce this different case of W evolution, so in the case when we have some mass, this situation quite close to standard analysis, because when because these modifications decrease the value of argument. So if there is mass, this decreasing is not so important. The analysis is very similar. But for another cases, situation is quite interesting. So high twist, not rise, but high twist change sign at the large values of x. So it was quite strange. And before when we do analysis with not so precise experimental data, we look only decreasing of high twist, like here, for example. But now high twist has changed sign, and but the coupling constants are very stable. So if we look, for example, scheme invariant theory, classic DJS scheme, so situation more or less same at next to leading coda. At next to leading coda, we only here change some cut experimental data, because for these cases we need quite large Q-square values, and Q-square values around 1. It's in this Q-square values about 1. At this Q-square values, we cannot solve equations for coupling constant. So we can see more or less same. So there is standard high twist more or less similar in the next to lead one. But for scheme invariant case, in deep analysis case, they are change and the same change sign. So this coupling constant, it's in standard case at next to lead one. This is after resummations. At next to lead one, it's standard one. It's scheme invariant case. It's in DIS case. So coupling constant very stable, but high twist change sign at large n. So it's next slide, please. So I came to conclusion. So we introduce some resummations, but to change factorization scheme and introduce x-dependent or n-dependent factorization scheme using by scheme perturbation theory, really Grunberg approach, DIS scheme, or several cases of W square scale. We show so coupling constant are very stable. It doesn't dependent of these resummations, but high twist values high twist are decreased, and really it allows large x high twist values to change sign. So the W square evolution obtained only at next to lead order, unfortunately, but some extension and for example, we work always for fixed flavor scheme. Number fixed flavor number scheme, but for variation flavor number scheme into next to lead analysis we hope to do quite soon, and we hope so basic property of this next to lead analysis will be recovered at next to leading level. So I finished. Sorry, but so I okay, but.
Okay, thank you very much for this presentation. Thank you. Do we have questions?
Can you hear me?
Yes, sir.
Sorry, because I'm sharing, I cannot see what I'm doing. Thank you for the talk, Anatoly. If you go to slide, 1 second, let me just, since I'm sharing. Can you please provide oh yes, I'll do it myself. Can you please provide more details on how you determine this uncertainty of about 2% on alpha S? How is this theoretical? Is this experimental? What does it include?
Yes, but uncertainty taken from a previous paper because it's from standard analysis. For another analysis, we did not study it yet because this we had no time. So in this case, all these uncertainties are same, but it's taken from this previous paper. This uncertainty, this is a systematical one from BCDMS because Krivohizhin is member of BCDMS. There was, and there are some statistical errors, and there's combination.
I thank you. And this data is used in the global fits. Maybe it's not a question for you, it's a question for the global fit.
But not for global fit, it's DIS fit. For non-singlet, for large X regime, so it's not global.
My question is if imagine that the PDG wants to incorporate your result, you do a full NNL analysis. My question is this like double counting? Because is this data already used to determine alpha S with some alternative method or not? Maybe it's a question for the global fitters. I don't know. Or maybe.
Sorry, I did not understand the question.
My question is that this neutron data that you're using. Is it used already in other analysis?
Yes, of course. I think it's, but we use it. They are separately, for example, but people use it together with another data, like part of a set of the data.
Okay.
Okay.
Maybe
there are more questions, I think.
Okay.
There are more questions. Simone, please.
Hi. Yes, I was trying to understand a little bit better the formalism used for the resummation. So, correct me if I'm wrong, but what you do essentially is you use a X or n-dependent scale for the running coupling so that you reabsorb the threshold logarithms into?
Yes, effectively, coupling constant will be n-dependent or x-dependent, same. Yes, because at every moment the modification is different because the argument of the argument is n-dependent. So this so in some sense, million moments it's a new coupling constant in some sense.
Okay, so I have a question and a comment. So the question is whether, so if you think about like some standard approaches, say like resummation in the way, you know, Catani and people set it up, would it be your method equivalent to what is usually referred to as next to leading logarithm accuracy? So if you count the log in the exponent, this is what you sum. And then the comment is that it may be interesting. So a few years ago, we did, together with a subset of the NN PDF collaboration, we did a fit of PDFs, including threshold effects. We didn't look at alpha S though. And so we'll be interested. And we did a fit, which was a global fit, but also a DAS only fit. And so we'll be interested to see whether.
Perhaps maybe you can send me this paper and I study and we will discuss, okay?
Okay.
Okay. Okay, wonderful. So thank you then very much again.
Okay, thank you very much.
And we move now to the next presentation.
It's a pleasure to present you some results regarding the strong coupling constant and PDFs. So I will be discussing a phenomenological interpretation of the CMS data presented in this very novel paper. You have the archive number here on the first slide. So from the CMS side, the contact person for the analysis will be my supervisor, Lipka. And first, to motivate this, as you know, to study QCD, the production of jets will be the fundamental thing to look at. And in particular, what we're doing here is to extract the strong coupling constant simultaneously with the PDFs. And we can also extract other QCD parameters and other standard model parameters, such as the top mass, if top data are included, and so on. And another important thing that I will be touching towards the end is indirect BSM searches. And we would expect in general that jets at high PT could serve as probe for BSM effects as well. And the rightmost plot here shows you the kinematic region that we will be looking at. So for comparison, the blue dashed band shows you the HERA data that we will be using in this analysis. And the gray band shows you the novel CMS13TV inclusive jet production data. So in total, all the data sets, aside the jet data, which will be used at the anti-KT parameter as anti-KT algorithm size parameter 0.7, we will use the HERA inclusive deep inelastic scattering data and the 13TeV triple differential TT bar cross-section data, also from CMS, and these were presented in a previous analysis. And the results have been obtained using the XFitter QCD analysis platform. I have also contributed to the development of this software, which will be seeing a new production release shortly in the future. For the theoretical predictions, so first of all, we do an analysis at NLO, where we have fast NLO QCD predictions. This will be improved to NLO plus NLL. And these references to the NLL jet and MAKS are given there at the bottom of the page. We will also include electroweak and non-perturbative effects via K factors. And the contact interaction contribution at the very end will be computed with CI jet. This will be used in a standard model effective field theory analysis. So for the jet production, the QCD scales are by default set to the individual jet transverse momentum, whereas for the CMS 13TeV triple differential TT bar cross sections, we follow the procedure of the paper where these data were presented in, and more details can be seen there, but the scale choice is a little different. And now for NNLO, so at the moment we will need to resort to K factors, and we have computed these K factors with NLO jet plus and NNLO jet. And again, the basis is the NLO that we get from fast NLO, and then apply these various K factors for the NNLO correction, Electroweak and non-perturbative corrections on top of that. And the CT14 NNLO PDF was used in the determination. So there is also a small uncertainty from this choice of PDF in the factor determination, and it's accounted for in the systematic uncertainties. And we will also be looking at scale variations throughout the analysis. So similar to Amanda's talk, we will have the usual 7-point variation of the renormalization and factorization scales with factors of 2 or a half. And these are, I would like to stress it that these are not fitted. We will just input these scales into FastNLO and other various programs used throughout the analysis, and use the 7-point variation to obtain an envelope for the scale uncertainty. Now, the first step of the analysis is to profile the PDFs. So this is a novel procedure which has gained some popularity recently. And the point is that this is not a full PDF fit, but rather takes some existing global PDF set, and then the nuisance parameters can be adjusted slightly so that you can get an idea of how that particular PDF set would change should you also have included the profiled data set in the determination of that PDF. So we will be looking at the CT14 PDFs at NLO and NNLO to see how the jet and the top data would possibly affect that. And the uncertainties we will consider in the profiling are the PDF uncertainties and the scale uncertainty from the envelope mentioned earlier. So looking at the NLO profiling case, so the leftmost plot would show you the uncertainty of the gluon PDF. The red band is the original CT14 uncertainty. And you see that by including the triple differential TT bar data, you get the blue band, which is a slightly improved precision. And the middle plot shows you the same thing, but now including the 13 TeV jet data. And the rightmost plot shows you both of these altogether. So you see that there is improvement from both of these data, and quite a bit more from the jet data. And overall, in the case where both of them are included, the improvement is very similar to just having included the jet data. And in the case where we profile using the TT bar data or both the TT bar plus jet data, it can be possible to profile the PDFs and the top mass and the alpha S. So sadly, due to technical limitations, this cannot be done simultaneously. For that, we will later have a look at a proper PDF fit. But in the profiling procedure, when you can profile one thing at a time, either the PDFs, alpha S, or top mass, when we extract the top mass, it is perfectly consistent with what was observed in the fit of the previous analysis. And now for the alpha S, in accordance to the previous analysis using the TT bar data, what you see on the leftmost plot, that's only really for illustrative purposes, since this is profiling and not a full fit, but you see the same trend as was observed in the TT bar analysis, that the alpha S value would really go down from the TT bar data alone. For the jet data, we get something that is very close to the world average, as you can see in the middle plot. And if we should include both of these data, you see that we kind of get something in between. So the jet data is kind of giving additional constraints that take the alpha S value up a little bit again in comparison to the very low value that you would only obtain by profiling the TT bar data. And also doing this at NNLO, the interesting thing to see is that only the jet data at NNLO would lead to a much smaller alpha S in profiling, whereas the improvement in the gluon PDF uncertainty, as you see on the left, is very similar to the NLO case. Okay, that's it for profiling. And now let us move on to the proper PDF fits. So we shall follow the approach of HERA PDF2. And since we have these three data sets, the jet data, the top data, and the HERA data, at NLO, we are able to use all of these data sets. But sadly, we do not have NNLO predictions for the triple differential TT bar cross-section. And therefore, because the data are a little different at the NLO and NNLO analysis, also the parametrizations have been reinvestigated in both of these cases. So there are some differences, and you can see the parameters highlighted in red are different in these two analyses. And the uncertainty contributions that we will have for the fits are first of all the experimental uncertainties just coming from the fit of like how the mathematical description of the fit. Sorry, there was some background noise. Okay, hope it's gone now. Okay, so the experimental uncertainties come from essentially the Hessian fit, just the mathematical description, and the parameterization uncertainties arise from adding or removing additional parameterizations to the starting scale parameterizations that you saw on the earlier slide. And the model uncertainties come from varying these various fixed parameters within their uncertainties. So the charm and bottom quark masses, the strangeness fraction, and so on. And again, we use the same scale uncertainty principle as previously in profiling, but this time the envelope is added within the model uncertainties. Now, for the results for the NLO fits, the alpha S value, as you can see, is somewhat higher than when profiling the top plus jets data. But nonetheless, it's in very good agreement with the world average. And the pole mass that we have fitted is again in good agreement with the previous result. There's not much change to the profiling. And if we have a look at the contributions of different uncertainties, you can see that the scale uncertainty quite clearly dominates in the NLO analysis. Now, the interesting news is that when you go to NNLO and fit only the jet data, the contribution of the scale uncertainty goes down quite noticeably. So in this case, the dominating uncertainty will come from the fit uncertainties. And as a usual comparison, we would like to examine how much the CMS data actually improve the fit. So if we would fit the same parameterization to only the HERA data or to both the HERA plus CMS data, you see that there is quite a good improvement for the gluon PDF in the case where we also use the CMS data that is shown in the solid blue band, whereas the HERA data only case is shown by the hashed band. And now, earlier on, I also mentioned that we will be having a look at standard model effective field theory. And the point of this analysis is just to examine the possible bias, which I'm sure you're mostly aware of, that if we would expect some BSM contributions in jet physics at high PT, but we also determine the PDFs using these same data, then there's a possibility that maybe some BSM effects would be absorbed into the PDF fit. Now, one way to assess this possible bias would be to compare the standard model fit to a standard model effective field theory fit. So we extend the standard model Lagrangian with contact interactions, ergo dimension 6 operators. So these can be purely left-handed vector-like or axial vector-like, just depending on how the handedness is allowed to change. And these will be color singlets in our analysis for the moment, and these corrections are only available at NLO for the time being. And the good news is that if you look at all these PDF plots you see on the right side, the gray band and the blue hashed band, which are the standard model and standard model effective field theory results respectively, they are practically in perfect agreement. So you can only see the experimental uncertainties contributions here in these plots, and all changes are within those uncertainties. So essentially, there is no risk of having absorbed BSM contributions of at least that kind in the fit. And the alpha S and top mass values that we would extract using the SMEFT fit are in perfect agreement with the standard model values in the Nlo analysis. So there was no statistically significant deviation from the standard model, but it's nice to make a comparison to a more usual type of search for contact interactions, because conventionally one would just fix the Wilson coefficient of the contact interactions to either +1 or -1, depending on if you want to have a look at constructive or destructive exchange, interference with the gluon exchange. So if we would interpret our fitted values as such constraints for lambda, then we get actually for the left-handed model very close to the most stringent comparable result, and actually even a bit higher. So the gray box illustrates our now unbiased limits at 95% confidence level for the scale of new physics. So that will be 24 TeV for the left-handed model, whereas the most stringent result was from Atlas using 13 TeV diejet cross sections, and they had 22 TeV in their paper. Okay, and now to summarize everything, so the QCD analysis is probing partons roughly between 10 to -3 to 0.5, and we have examined the data and data's impact on the CT14 PDF set, and we can now explain that if we add the jet data to the top data, the previously seen very low value of alpha S is shifted up and goes closer to the world average. And then we have also investigated the NLO case using SMEFT predictions, and these are perfectly consistent with the standard model, but as a novelty, we have now got some unbiased limits for the contact interactions. And again, no difference seen in the standard model and standard model effective field theory fits alpha S values. And as perhaps the most important result, particularly for this conference, would be the NNLO fit for alpha S, which is the most precise value to date obtained in such an analysis. And you can see a combination of several measurements on the plot here on the right-hand side. And the analysis that I just explained about is now given as the last red line of the plot. So thank you very much for your time, and I would like to wish everyone a happy Chinese New Year.
Okay, wonderful. Thank you very much for this very interesting presentation. Let's see, there is a message in the chat. No, something else. Okay. So do we have questions for our speaker? I see a hand by Bogdan.
Yes, hello. Thank you for the very nice talk, Tony. So I actually have two questions. The first one, for the K factors, for the N2LO K factors, do you have them for some fixed alpha S and PDFs, or do you have some scan? How do you deal with them?
Okay, so we determined the K factors with the CT14 set. So in CT14, alpha S is 0.118, but I'm not quite sure if I understand the question.
But aren't you worried? I mean, so you don't have a scan as a function of PDFs, you don't have a scan as a function of alpha S, if I understand correctly. So you fix them in the K factors, but afterwards you do fit PDFs and you do fit alpha S. So you probe a series of values there, while the K factors are fixed.
So this would be the case practically for all sorts of K factors. So if we use a K factor, there's of course always some kind of an assumption about the behavior of the K factors. So whether it's the NLO K factor or NLO plus NLL or whichever K factor, you would assume that the difference between the NLO result and the NNLO result would be sort of independent of various things. So actually, so when we fit for alpha S, the important thing is that there is a part in the analysis framework that takes care of alpha S evolution, right?
Yeah.
But this is kind of independent of the K factor. So if you have your analysis framework with the alpha S evolution running at NNLO, and then you compute a cross-section, you start with some NLO result, and then you just want to somehow estimate how you turn this NLO cross-section into an NNLO cross-section, then you would use the K factor for that.
Right. What I meant is just that, for example, scale uncertainties, they are not really at N2LO in that case. I mean, just this is what I had in mind.
Yeah, not really. And actually,
maybe to interrupt here. So the K factor is of course known for different scales. That is included when you use different scales. The dependence on alpha S itself is totally negligible in the K factor because it's a ratio of two expressions that have the same leading term in alpha S.
Exactly.
There is some remaining one on the PDFs, but this is rather small.
Yeah, I mean, formally it's really higher order what the alpha S dependence in the K factor here.
And maybe I also can comment here to make the long story short. We also looked into the K factors obtained for different PDFs, and for example, CT18 and ABMP16 have completely different alpha S, and the effect is negligible, as Klaus said.
Yeah, I mean, when you say it's higher order, I mean it's N2LO. That's the higher order. So
No, it's N3. It's N3 in this because so these ratios, no, unless I mean the sigma NLO is the same as sigma NLO up to order alpha, right? So these expressions differ already We can discuss. We can talk about this in the discussions. But I think this is really alpha cube. That's
I'm surprised by that. But anyway, I had a second question. It was about the fit quality. Can you comment? I mean, on the chi-square by degree of freedom that you get. What is the value? I saw the absolute values, but I didn't catch the ratio.
So I don't think I have listed the chi-squareds here. We have them.
The chi-squared are listed in the paper, Bogdan. So if Tony doesn't have them, these are in the tables of the paper.
But are they good? I mean, can you comment on the values?
Yes, they are good.
So without theory uncertainties, they are good.
The theory uncertainty is not fitted.
Right, but what I mean is that, so if you get good chi-squares without theory uncertainties, we know that the chi-squares are quite sensitive to the theory uncertainties. So in a data to theory comparison, you would get essentially a 2 good chi-square if you were including them.
So what you're asking is what is the chi-squared for the individual fits when you vary the scales, or what?
What I'm asking is what's the chi-square with or without the theory uncertainties in the 2 cases?
Well, the theory uncertainties are not fitted.
So then once again, I mean, if you were including them, my point is that it will get much better, basically. So probably maybe too good, but okay, it was a remark.
Yeah, but the scale uncertainty, as we said, is not fitted. It's not included in the fit. It's rather at each time of the scale variation, the alternative fit is performed.
Okay.
Because we don't want to fit the theory uncertainty. However, what we don't have in the paper is the chi-square quality of the individual fit for the different scales that we don't have. I mean,
this is what I
internal information. That is, I mean, I think that is no secret. We can this to you, just finding back the chi-squared for the individual fit.
Okay, thank you.
Okay, maybe we should, okay, Daniel, one last question.
I just have a tiny comment. Maybe if you go to the summary, it's very obvious then. I also stuck there in the paper. I think you should first do the SMEFT analysis and ensure that the data is described by the standard model. And only then one can determine the standard model parameter. Because, I mean, if you determine alpha S and then you find in the SMEFT analysis that there's BSM contributions in the data, then the IFS cannot be correct. So basically one should turn around here the way how these results are presented.
Well, we first wanted to present the results at next to leading order. And for that, we don't have the SMEFT contribution.
Yes, indeed.
The CI jet is next to leading order.
Anya, if you would have discovered new physics, the paper would have been published differently, right?
Yeah, exactly.
At least it would have a different title.
Okay, maybe we should now really move to the next talk.
There is Andreas who had a question.
Sorry, Andreas. Yes, Andreas.
Hi. I just wanted to amplify that remark about doing the SMEFT first. If you think your data have new physics, you should marginalize over parameters that describe that new physics. It's the same with any other systematic effect that might pollute the data.
Well, in principle, the paper content, so the standard model and SMEFT analysis are individual analysis. So it's not one built on top of another. Exactly. So there's a completely individual. So basically, first we do the standard model analysis next to leading order, as any PDF fit does. And then alternatively, we start from 0 and performing the SMEFT analysis. So basically what you're saying, it's just the order how the results are presented, but I think it's not really important.
Well, I think the previous questioner and I understood that, but I suppose this would be a different way of analyzing the data. I mean,
well, using the JET data at the LHC, that is the first analysis of this kind. So how we present the results,
I think neither one of us is complaining about either one of the analyses. But if you have data that you think contain signals from new physics, that should be incorporated somehow into the final result for alpha S.
But it is.
Ah.
The result of the SMEFT analysis includes everything. So that is one simultaneous analysis where the standard model Lagrangian extended to EFT contributions. And in this analysis, of course, to the extent the theory allows that, for example, only color singlet EFT contributions are included, you extract the Wilson coefficients for the different lambdas, you extract the PDFs, alpha S, and the top quark mass all simultaneously. That is not that we build on top of the standard model analysis. The SMEFT analysis is the absolutely unbiased analysis where everything is determined simultaneously. That is the difference to all the previous analysis for the context interactions.
Okay, sorry, I think then I misunderstood. The SMEFT analysis is exactly what I think the previous person was suggesting and that what I was suggesting. Sorry about that. Thanks.
Okay, thank you. Okay, so thank you very much. And let's now move to the next presentation. David, okay.
Yes, can you hear me?
Yes.
Good. I will be presenting today the analysis that were published about 2 years ago, first in a CMS paper, and then we extended this analysis to the full LHC data at the time. The idea is to extract alpha S from an NLO analysis of the inclusive electroweak boson cross-sections at MPP collisions. So the method, the idea is as follows. We calculate the inclusive W plus, W minus, and Z production cross-sections within the fiducial volumes measured at the LHC at NNLO, and then we compare them to the experimental data. And then from that, we can derive alpha S. Of course, if you look at the matrix elements at leading order, there is no dependence on alpha S, of course, because this is a pure electroweak process. But as soon as you include NLO diagrams and NNLO also diagrams, you start to see gluons showing up, and that's the dependence on these gluons that brings in the dependence on the electroweak boson cross-section on alpha S. Of course, the PDFs themselves at NNLO have a dependence on alpha S themselves already. So to give you an idea, the fiducial cross-sections, because at face value you think, okay, I mean, why W and Z bosons are sensitive to alpha S? You realize that the weight of these diagrams is not negligible. It's between 20 to 30% at the LHC. So it means that there is a sensitivity to all these gluon contributions and thereby alpha S. So, and then of course the main motivation is that the W and C cross sections are the most precisely known at the LHC, both experimentally and theoretically. So experimentally, statistical uncertainties are basically negligible now. They're below the few per mil level. So we are right now, we are dominated mostly by systematic uncertainties, and here the luminosity, integrated luminosity dominates. It's about 2%, in some cases even below, more recently. But the data we analyzed was 28 leptonic fiducial measurements made by a CMS, LHC, and Atlas, and you have the list here of cross sections that were measured. So for example, WE plus in the electron channel, or I don't know, or Z average over muons and electrons, and then different regions of phase space and so on and so forth. And then theoretically, this is known at NNLO. Actually, it is known now at N3LO, but since we don't have PDFs at N3LO, for the moment, the best we can do is an analysis at NNLO accuracy. And here the scale uncertainty is already pretty low. This is 0.5 to 1%. Of course, the theoretical uncertainty, the dominant one, is the PDF one. It's 2 to 4%. So that's why we will carry out an extraction of alpha S per PDF set to gauge the impact of the PDF uncertainties. So that's the idea. We compare 28 all these measurements to the NNLO prediction, and we try to extract alpha S if possible. That's the idea. So to do this, so this was done with a couple of students, well, mostly one student of mine a few years ago. We ran MCFM, which is the fastest calculator now in the market. We can define, we define each one of these fiducial volumes, which is different for the leptonic decays, and we compute cross sections at NNLO. Then we interface MCFM to 4 PDF sets, CT14, Hera PDF 2.0, MHT14, and NMPDF 3.0, with all the associated eigenvectors or replicas. And I want to stress something already at this stage, because this is something that has to be clarified up front, I think. None of these global PDF fits included the absolute cross-section values here that we exploited to start alpha S. So really it's an independent extraction of alpha S if you want, because none of these PDFs included any of these data sets. Some of them, including 1 or 2, I think, differential shapes, but not the total integrated cross-section. And then of course what we do is we run for 7 values of alpha S from 0.115 to 0.121, and we try to find the minimum. We know that there are for Electroweak bosons we have non-negligible Electroweak corrections, so those are computed with MC-Sank, and then basically what we do is we compute a multiplicative factor that tells you that the impact of these corrections, and is often negative. And it's a few percent negative correction on the overall cross section. So as I said, we had all these data sets for 7, 8, or 13 TeV, all these total number of measurements. So this represents 28 systems, and this amounts to 20,000 jobs, taking into account all the PDF eigenvalues, 100 for NPDF, 56 for CT, well, 50 also for Hera PDF, 50 plus for MMHT, and then times 5 to 7 alpha S values. So you start to multiply. It was a lot of work of bookkeeping, mostly, as you can imagine. So running at an NLO is fast in MCFM, but still, I mean, it took 2 weeks to get 2 to 6 per mil numerical accuracy, which is comparable to the 1% differences that we found by running different calculators at an NLO, like Fuse or DY and NLO. I will comment on this later on at the end. So this is an example of a table in our paper. So you see here, for example, a given Atlas measurement, say PP going to W plus at 7 TeV within this fiducial volume. This corresponds to 2.947 nanobarns, plus minus whatever. And then this is the result that we obtain with MCFM at NNLO for CT14, Hera PDF, blah, blah, and the correction for MC-Sank. You have all the values here. Just to give you an idea, again, let me stress the importance of the theoretical and experimental uncertainties. So the leading uncertainties are luminosity in the data. Systematic ones are smaller, 1 to 3%, Lumiere 2 to 4%, smaller depending on the measurement. Statistical are negligible, basically. In the theoretical side is 1 to 4% from the PDF. Scales are 0.4 to 1.2, and numerical, as I said, is about 0.5%. And then just to let you know, if you take the default alpha S 0.118 for each one of the PDF sets, and you calculate the 28 cross sections, and you determine the goodness of fit by the chi-square per degree of freedom, you find that for this default alpha S value, you get basically quality 1 for CT14 and MHT14, and here PDF and NPDF 3.0 were somewhat worse. You will see this now in detail. So how do we extract alpha S from this? So what I'm showing here is the dependence on the x-axis of alpha S on the cross-section. So and then here on the horizontal line, you see the experimental value. That's the value, for example, for Atlas. What is this? W plus at 7 TeV. So this is the measurement, and this is the experimental uncertainty, mostly driven by luminosity. And then this is the predictions for theoretical predictions for the cross section for varying values of alpha S. So you see how the different, of course, the bigger alpha S, the larger the cross section is. So you see all this slope, all this positive trend. And this here tells you the theory uncertainty, which is mostly the PDF uncertainty. So the point where those two lines cross is the alpha S 0.118, which is the preferred alpha S value of the PDFs, also the world average at the time. And then this is the cross-section experimental value. So the point where both lines crosses, this is the this would indicate a perfect match of the theory for alpha S 0.0118 to the experimental value. So you see that sometimes the theory prediction goes to the left or to the right of this thing. And the 1 sigma ellipses are joint probability density functions derived from the product of data and theory uncertainties. So this is for Atlas data, this is for LHCb data, this is for CMS data. You immediately see that the trend is for more CMS data. So you see the cross-section, as I was saying, the cross-section rises with alpha S, like this, for HERA PDF, like this for MMHT, for example, and so on. And you already see some generic trends. Theory predictions are consistent with data within uncertainties. You see here, those are the uncertainties, of course. Okay, is there a comment, question? Okay, I continue. It is not systematically the case that the theory prediction is consistent with the data for a fixed value of alpha S. So for example, you will see here a PDF keeps mostly jumping a bit to the left here, whereas other predictions are more stable. For a fixed alpha S value, there is a hierarchy of results where HERA PDF predicts a larger cross-section. So you see here, for a fix, you take a fixed value, say 0.118, you see that the central value from HERA PDF is 2,280 picobarns, whereas the one from MHT is 2,200 picobarns. So you see the difference. So in general, the trend is that HERA PDF prefers systematically smaller alpha S, and NMPDF, which is here, prefers larger alpha S. Okay. To reproduce the data. And MMHT and CT14 are somewhere in between the two. And then the third observation is that HERA PDF has the smallest slope, so it's the shallower shape. Is the dependence of the sigma from HERA PDF is flatter than for MMHT. MMHT is steep, so it means that MMHT has a strong dependence on alpha S. So it's much more dependent on alpha S than HERA PDF. That's the observation. Okay, with all these elements in hand, we then determine the preferred alpha S per measurement. So the preferred value is this is just a cartoon. The value where the experimental cross-section crosses the theoretical one. This is our preferred alpha S. And then this is the theoretical, and this is the experimental uncertainty that you can propagate to alpha S properly. I don't go into the details, but it's easy to propagate. And then that's the type of result we obtain. This is a subset of all the alpha S extractions per measurement, and per PDF we have 112 values like this, where we have a given measurement with a given preferred alpha S with a breakdown of statistical, luminosity, systematic, PDF, scale, and numerical theory uncertainties. You have them here. So for all the 4 PDFs and so on. As of course, the dominant propagated alpha S uncertainties are luminosity for the experimental part and PDF for the theory. But you have here all the values that the theory prefers to reproduce a given experimental result. So once we have these 28 measurements, 28 values of alpha S derived times 4 for 4 PDFs, then we combine per PDF, we combine them using Convino to take into account the correlations and the uncertainties. This is equivalent to the blue method, but this takes into account asymmetric uncertainties. That's why we use this tool. So it's important to account for all the uncertainty sources, and their correlations. Luminosity, which is the dominant one in the experimental site, is fully correlated within one detector and one square root of S. Otherwise, it's uncorrelated between detectors or between different square roots of S. Statistical uncertainty as well as numerical uncertainty are fully uncorrelated, of course. Systematics and you will see next slide, they are partially correlated. And theory and PDF also, you will see, I have some details next. So here you have a typical experimental table with the percentage of uncertainties from different sources of systematics, lepton reconstruction and trigger, energy scale, blah, blah. So that's a breakdown for the different measurements. And of course, there are intra-experiment correlations of all these sources of uncertainties. And this is what we did. We computed the correlation matrices for the intra-experiment measurements. So for example, you see here the correlation matrix between W plus, W minus, and C for Atlas at 7 TB, here for LHCb at 8 TB, and so on and so forth. I don't go into the details, but we in principle, we propagate this properly. And then in the theoretical side, there is a correlation of PDF uncertainties for within any given alpha S value extracted within the same PDF set. You have, of course, a correlation of the PDF uncertainties. So the way we determine this is via Pearson correlation coefficients calculated from all cross sections, computed with all individual replicas for each pair of W plus, minus, and C measurements, and then we find a correlation which is between it's half correlated for CT14. Also a little bit correlated for MHT14. It's the correlation is higher for HERA PDF, and NMPDF is almost fully correlated. That's at least what the this quantification based in this method that tell us. In order to check the stability of alpha S with respect to the assumed degree of correlation, we arbitrarily took 0 correlation or 1 correlation, or correlation 1, sorry, for the PDF uncertainty, and we derive alpha S values, and you see here that it does not change much. This is the Pearson correlation range determined for a CT14. This is for HERA PDF, MMHT, and NMPDF. We do the same for the scale uncertainties. And again, depending on the PDF, we find Pearson correlation coefficients between 0 to 0.8. Anyway, you see here that the dominant theoretical uncertainty is PDF, and you see that the alpha S value is constant with respect to, basically constant with respect to the amount of correlation assumed. But we will propagate this properly as I will show you later. Okay, so now this is our final result. We have 28 alpha S extractions and their average per PDF set. So this is here in, for example, in red, you see the HERA PDF results, and you see their average here. You see HERA PDF is around 0.110 with a 2% propagated uncertainty, whereas the other 3 global PDF features are closer, are scattered around the whole average with uncertainties which are in the 1% ballpark. Okay, we did some robustness tests with respect to the, we check what is the dependence of the alpha S extracted on the experimental and theoretical ingredients in their uncertainties and in their correlation. So we did many different, we ran many different analyses variations. So for example, from the experimental side, we just took data at 7 TB, or just data at 8 TB or at 13 TB. We only take Atlas data, we only take and so on, LHCb, CMS, and you see how, for each case, how things fluctuate. You see, for example, that MMHC14 is very stable. I mean, you see, for example, that we just by keeping a subset of data, you get the same alpha S. The same is not true for other PDFs, that you have more, you have a larger scatter. Then we, as I said, we varied the correlation assumed for the PDF and the scale uncertainties between no correlation and a full correlation, and you see the results here. PDF is row 1, and so on. What we did also is, this was a proposal of one of the referees, is that we shift first the central values prior to the combination by ±1, and then, so in a way we redo the combination of with Convino of all the alpha S estimates, but shifting first the central values by 1 sigma of the theoretical uncertainties, and see what the result is, depending on, so you see minus theory uncertainty shift, no theory shift plus 1 theory shift, so you see the type of changes that we get. And then we add also 1% theory uncertainty, just if you want arbitrarily, to account for differences that we found by running alternative calculators, Fuse and DY and NLO, and how these change things. The takeaway message is that things are stable within the assigned uncertainties. So you see that I mean, of course, you have some outliers, but on this is expected. On average, everything agrees well within the assigned 1 sigma alpha S average of per PDF set. So with this, we get to the final result. So this is the final alpha S values per PDF with a breakdown of the propagated uncertainties, as well as the chi-square per degree of freedom of all the so basically of each one of these 28 individual results with respect to the central value that derived. You see that things are around 1 for CT14, HERA PDF, MMHT, not for an PDF 3.0. There is some issue here with some outliers. Okay, we can discuss this. You see that they tend to be to the left, so the individual values, whereas the average is to the right. This is because of strong correlations between some results in the case of an PDF 3.0. At the end, by looking at all the PDF extractions, we claim in our paper that we prefer the MMHT14 result for 4 reasons. First of all, it has the largest sensitivity to alpha S. If you recall the plots previously, the slope of sigma W plus W minus and C to alpha S is the steepest for the MMHT, so it's the most sensitive to alpha S. It has a better chi-square of the combined values with respect to the central average. It has the lowest propagated uncertainty, and it is the most robust with respect to the analysis variations. You see here that the scatter here is smaller than other sets. So this is why we, at the end, this is the comparison of this is the parabola, the minimum parabola of the 4 PDF extractions. And then this is we single out here the MMHT14 one, which for this particular analysis we find is the most stable. So I come to my summary and then 2 slides for discussion if you want. So what I presented today is this new alpha S extraction from high precision inclusive electroweak boson cross sections at the LHC. We use 28 data sets up to 2019. So we have more than 100 individual alpha S values at Nlo derived per. So of course this is for PDFs, it's 28 per PDF. And we combine them, accounting for propagated experimental and theory uncertainties under correlations. We find those results. You see the plot here. The minimum, this is the world average at the time. Now it's a little bit 0.1179, but okay, it's very close to this. And we know that last year the PDG world average, they decided to incorporate this result into their categories. So this is for the summary. Now let's go to the discussion, because this is things that have been already mentioned before. I mean, this extraction of alpha is based on the inclusive W and C cross sections that I presented has been criticized by Forte and Casavov. Also, Juan Rojo today mentioned it, this paper. But I mean, first thing I'd like to clarify the semantics. I mean, I don't know why Joan was emphasizing that there is no alpha S preferred by a given observable. In reality, we do not care if this term is valid or not. What we would like to know is what would be the global alpha S fitted by a given PDF global fit analysis if a given extra observable was incorporated into the global fit. So say now if NMPDF 5.0 incorporates the inclusive WZ cross sections, what would be the alpha S value that they would fit? In a way, he was saying that this, I don't know if he's connected, Joan, anymore, but he was saying that claiming that this ZPT alpha S preferred value is wrong, because this depends on a PDF that accounts for the rest of observables. So be it. I mean, we don't. The goal is not to have an alpha S preferred by a given observable. The goal is, let's assume that we have this extra point there. Does this combine with the rest and brings a more precise alpha S value with reduced uncertainties or not? That's a question we need to answer. And the question is whether the method, whether incorporating this here is equivalent to doing a global fit or not. That's a question we have to address. So this is the first comment about the semantics, but then let's go into the details. So if this method has been criticized by Forte and Casavov that one cannot determine alpha S from hadronic processes without simultaneously determining the parton distributions, this does not just affect this sigma W and C extraction. It impacts also the TT bar, sigma TT bar, and also the Hera jets results. So basically, I think all the hadron colliders are affected by this. They should be incorporated into the global PDF fits, and this category should disappear from the PDG. The question is, the important question for us is that for now, these 28 inclusive fiducial cross sections are not today into the global fits. So those are extra information that is provided there, and that then this is not there. So one cannot claim that this is an information that is added into the system. So the alpha S is independent of the PDFs. So I think this is valid still. And then we have the discussion we had previously of the intrinsic theory uncertainties, missing higher order uncertainties. So that are still there in the global fits and they are not properly accounted for. So this independent alpha S extraction with inclusive fiducial cross-section is a useful cross-check. At the end of the day, I think that take-home message is that probably the most accurate thing and most appropriate and most consistent thing is to incorporate consistently all these observables into the global PDF fits and then derive alpha S with this information incorporated. And the question is, can this be done? And if it is so, how can this be done and when will it be done? Thank you.
Okay, thank you very much, David. So let's see, do we have questions for David? Yes, I see many
I have
hands.
a question, Julia.
Yes, maybe we start by, okay, Sven is already unmuted, yeah.
Yeah, I have a comment, David, to your talk. Basically, you're using MCFM as a code. You try to evaluate this to NNLO, but there are problems with these differential codes, and you do have to do fiducial cuts, of course, due to the lepton acceptance cuts. There are problems with the accuracy of these codes, and in particular those that use global slicing methods for the regularization of the double real emissions. And in particular, MCFM is a code that can have very large deviations, much larger than the size of the NNLO correction itself. So depending on the kinematic cuts, it can be up to 5–10% deviating from codes which use local subtraction schemes. And therefore, I'm afraid to say, but the code is not really reliable for the type of investigation that you envisage here. Other codes like Fuse, which implement a local subtraction scheme, they don't suffer from this problem of linear power corrections there, and therefore they can be considered reliable. Recently, Matrix has also been doing some effort in order to account for linear power corrections in their code, so they're improving. I think one really has to look also at the accuracy of the theory calculations that go in there, and the tool that you have chosen, I think, is a bit on the problematic side.
Well, we did this type of careful cross-checks that you're asking, and we didn't find differences beyond 1% for Atlas and CMS. So we found identical results running Fuse and DY and NLO. We did find differences for LHCb. For LHCb, Fuse and MCFM, they differ by 1 to 4% in some cases. But the problem is that we did not have access to the exact input cards that they use for Fuse. And we think that actually the problem is not in the slicing procedure for NLO corrections and so on. The problem is a more prosaic one, if you want, is that is as simple as the branching ratio of the leptonic branching ratio is not identical in all codes, and this can easily introduce a few % differences. So it's much more prosaic. The total cross section is what it is, but then when you decay and you take the branching ratio, the width, the leptonic width, is not identical in the different codes. But we didn't go into all these things. Just to let you know, we checked for Atlas and CMS. And we found uncertainties differences below 1% for this. We compare Fuse and MCFM for LHCb, and we find difference of a few %, 1 to 4% at most, that we did not investigate beyond that. But so what I'm trying to tell you is that if I was to repeat the analysis with Fuse, I'm pretty convinced that we would get a very similar result.
No,
and this was one of the reasons why we incorporated this extra 1% uncertainty.
I think this is not correct. There has also been theory work by Tuckman, Ebert, and Stewart in the last years who really show analytically how these power corrections arise, and you can really trace them down as appearing in those slicing codes like MCFM, like Matrix, and this is the real source of uncertainty. And of course, you have to make sure that the input cards are all the same with the same parameters. Yeah? So this is a real problem for what is currently available as public codes.
We did this check. I'm telling you, Sven, I'm telling you that we did this check for CMS and Atlas, and we found results consistent within 1%. For our fiducial cats. I don't know if there are other fiducial
then I think you're contradicting what we put out in the paper last year, where we detailed this, also looking at precisely those data that you are considering here. So I think this is a big problem. Yeah, I mean, it's a big problem. You're not the one to blame, because you're using theory codes.
But even even take a look. I mean, you add a plus 1% uncertainty in the theory side, or a minus, and you get the same alpha S. That this is very robust with respect to this.
I think the uncertainties are actually much larger. This is the problem, yeah. So this is where theory really has to deliver.
Does this not depend on how you run NCFM, on the precise settings that you have in the slicing parameter? Huh?
No. You can really go down to very low tau cut values. I mean, basically, then it depends on the runtime that you want to investigate, but it doesn't converge. This is not with a machine, not with a precision currently hard coded. You would probably have to go to quadruple precision or even higher, but this is not what's being delivered by MCFM. So the tau cut values that you have to choose, that you would have to choose in order to really get precision, the same accuracy as a local subtraction code, this is currently not to be realized on.
But take a look. I don't trust that this will be larger than the PDF uncertainties, and this is the experimental uncertainty. So if you tell me now that if I run Fuse, and I don't get this thing here, I got something completely off up there, I don't believe you. Sorry.
We can take it offline. I can point you to the paper.
Okay.
Thanks.
Okay, good. Yes. Thank you, Sven. So then we had a question by Simone.
Yeah, so there are a couple of general points maybe. So maybe first on your last slide, and also about this paper from NNPDF. I tend to agree somehow with the point that you may be underestimating the uncertainty due to the correlation with the PDFs, right? And this you see actually in your results, since the number that you get from each different PDF does not overlap within the uncertainty. And but I mean, this is, I think, a known and solved problem, right? You put everything in a PDF fit, you redo the fit, and you get an unbiased result for alpha S. I mean, that's what was discussed in the previous talk for a experiment-specific result, and what also all of the other global PDF fitter discussed.
But yes, I mean, nobody disagrees that the ideal case would be to incorporate all this data directly into the global fit and redo everything, the PDF and the alpha S fit, in one shot. The question is, how do you include that at the total inclusive cross-section? For example, in many cases, they just take the differential shape because
so that would have been my second comment, because I'm pretty sure that some of the cross-section that you included were included in the PDF you used. They were included as differential cross-section, but that's the same, right? I mean, you add up the numbers and you get back the total fiducial cross-section that you used. And
only 2 of them or 3 of them, and not in all PDFs.
That's true. But yes. But what I mean is that by adding the differential distribution, you are only adding information, not removing, right? In practice, you keep exactly the same information you have used, and you add a little bit more that is the shape of the distribution.
But then how you deal with the absolute normalization? I mean, if we have high order missing corrections.
Yeah, but okay, but that's a general problem for the PDF. That's what also was discussed for jets. Exactly. But you also have the exact same problem, right? Because you also have missing higher order uncertainties that you need to include in some way. So the only thing that you avoid is to say this PDF dependence on the K factor if you want. But that's again higher order correction. So in principle, it's not an issue at the order at which you are working.
Mm-hmm. No, I think, I think we I think we should agree that all this category hadron collider should disappear, because at the end this depends on the PDF, and this should be somehow incorporated here.
But I think I'm not expert on all of this, but I think most of these results do a simultaneous PDF fit.
Okay, sorry to, Klaus, you had a question?
No, this is exactly my comment. So your answer here, David, is too simple. You did not look precisely enough in what is included in this category. It's not that these here do not contain PDF fits and the upper part contains PDF fits. For example, let's take the Hera jets, which is below your approach. In the Hera jets, and Daniel will explain this a little bit more elaborate tomorrow in another context, it just assumes the X dependence from one particular PDF set, including uncertainties, or the evolution, including the alpha S in the evolution, everything else is included in the fit. That is not the case in your case. So the fit that is used in Hera jets is much more elaborate. And then secondly, the H1 jets result is including a full PDF fit. So they are not all at the same level of sophistication in terms of alpha S fits. So simply saying this should be included is not the right answer.
I'm not saying that you should put this category in here and merge it. No, not at all. What I'm saying is that you should include, maybe I didn't express myself correctly. What I'm saying is, let me see, because I tried to phrase it, incorporate the observables, namely incorporate sigma TT bar, incorporate sigma W, sigma C into the global fits, not incorporating these extractions, incorporating the observables directly, and then these people redo their fits with this sigma TT bar, jets at H1, Hera jets, sigma W, sigma Z at the LHC, all these observables. I'm not saying incorporating this here doesn't make any sense. I'm saying incorporating the data into the global fits.
David, I'm sorry to interrupt the discussion, but we have a discussion session later. We have still one talk. I think we should now move to the next talk, and maybe we can in the discussion session even pick up on your slides. But
sure, no
I think we should now proceed with the last talk. Okay.
So thanks for the invitation to talk about this. The latest PDF determination by the Atlas collaboration, which is called the Atlas PDF 21 fit. So the Atlas PDF 21 fit is a PDF fit to multiple Atlas dataset, and with this fit we made the attempt to simultaneously fit as many useful Atlas data sets as possible. Of course, the DIS error data are the backbone of our PDF fits, and we added Atlas measurement from different square root of energies on top of them. Error, of course, is the backbone on our Atlas PDF fit, because they provide a constraint on a wide variety, a wide range of X and Q square, while the LSE data provide additional constraint in the medium and high X and Q square range. In here, slide number 2, you have a table with all the data set and the distribution entering the fit with the square root of energies and the corresponding luminosities. So slide number 3 here, I'm listing all the advances with respect to previous Atlas PDF fit. As I told you in my previous slide, this is the first Atlas PDF fit which aimed to include many Atlas datasets, in contrast to the previous PDF fits where we were including error data plus 1 or 2 other Atlas datasets at a time. Is the first Atlas PDF fit which includes 13 TV data, and not only the first Atlas PDF fit, but for at the time being only an NPDF 4.0 include 13 TV data. We include scale uncertainty as additional correlated systematic uncertainty, of course, where they are relevant. So, for example, for the WZ data 700 TV, because these scale uncertainty are at the same level with the experimental uncertainty. We perform a detailed study of the correlation between the various Atlas datasets. So we gain experience on the Atlas systematic uncertainty treatment to make a proposal, so also global fitters can use this vademecum to properly treat the correlation between the uncertainty on the Atlas data. We extended the PDF parameterization. So this is the first time we have more than 23 parameters. Keep in mind that previous Atlas PDF fits were just with 15 or 16 free parameters. And this is the first Atlas PDF fit with an enhanced tolerance, which has been determined using the the MHST dynamic tolerance procedure, but I mean, you will hear more about it later. So in slide number 4, I would like to show you the theory framework of this work. All the fits have been performed using XFit, and all the results have been cross-checked with an independent fitting code known as the Oxford code. As regards the theory prediction for LAC cross-section, they come directly and next to next leading code from fast Nlo, or I mean, we achieve next to next leading code accuracy from next leading code the prediction from operating through K factor. And here you have a table in the middle of the slide with all the code used for next leading code accuracy leading code electric prediction, and also the code we are using for achieving state-of-art precision for this theory calculation. So next and next leading code accuracy and next leading code in electroweak. As I already told you in my previous slide, this is the first data suite where we also include scale uncertainty, and they are applied as an additional correlated systematic uncertainty only in the case where the data effect is compatible with the experimental systematics. And of course, in this work, we also evaluate the impact of the scale uncertainty for other data sets, but it's found to be negligible. As regards to PDF formatization, we use the usual form using also in the ERA paper. So we have the nominal term, which is x to the b 1 minus x to the c, and then we have more parameters to describe the PDFs to give more freedom to the PDFs in the IX regime. We've also next negative term just for the Gluon PDF. So we parameterize 6 different PDFs, as you can see here in the third bar, at an initial scale of Q0 square equal to 1.9 GV square. As I told you, the central fit has 21 free parameters with a fixed value of alpha s equal to 0.118. So we do not have any constraint on the A and B parameter on the C quarks, and as well as no constraint on x du bar and minus x nu bar, and on the ratio to the strange to the light C quark as x goes to 0, either in shape, and these no constraints are either in shape or in normalization. So in the last bullet of the slide, I'm also listing the model assumption and uncertainty. We are assuming the epical mass to be, the charge mass, the charm quark mass to be 1.41 GeV and the bottom mass to be 1.2 GeV square. We are considering data with a cut on the minimum Q square, so equal to 10 GeV. And also, we are assuming the top mass for our prediction to be equal to 170.3 GeV. And of course, we vary this model assumption to assess model uncertainty, but I have a slide about it later. Slide number 6 here, I'm showing you the results for the chi-square. So you can see we have a pretty good description over 1,600 data points. You can see here, and here I also split the chi-square for different kind of data set. We have the W7 and 8 TV. We have the direct photon data and the V plus jet and the inclusive jet data. So I don't want to go through in the detail of all these numbers, but I can tell you that the fit achieved here in this paper is better than the one achieved by global fits to this data. We are not. I'm not trying to say that we are trying to compete with global fitters, but I just want to say that we managed to have a pretty decent, a pretty good description of this data with our fit. So the great novelty of this fit is that we made a thorough study on the possible correlation between the ATAS dataset, and we carefully investigated any possible correlation between our data. So here in the table, I'm reporting systematic uncertainty in the first column here on the left-hand side, and here the various data set entering this correlation exercise. So we have here for the first two columns the ATV V plus jet data, then the third and fourth column represent the TT bar data, profile data, and ATV, and the ATV inclusive jet. We are including in our fit. How you should read this table? I mean, the entries in the same row are taken 100% correlated between the V plus jet data and the TT bar jet data because they are using the same sides of the radius for the jet definition. While we also investigated different degrees of correlation between these four datasets and the inclusive jet dataset, because I mean the different jet choice of the radius they use are equal 0.6 with respect to which is different from the one used for V plus jet data. We also we also performed these studies, and I can tell you that the exact degree of correlation between the inclusive jet data and the other dataset here, does not change the resulting PDF that much. The really important stuff is the correlation between the V plus jet and the TT-bar data ATV. But here, slide number 8, I would like to show you the impact of the correlation between on the PDFs. And here you have the gluon PDF and the D-valence PDF at the starting scale of 1.9 GB squared. As you can see, comparing the two curves, you can see that the correlation, the inclusion of the correlation does not give a big effect on the PDFs, which are always compatible within just experimental uncertainty. Of course, the difference is more visible if considering the chi-square. For example, the fit without taking into account the correlation, X beta and more is kind of about like 30 units. But anyway, you can see also here, at slide number 9, where I'm showing you the same two plots of the previous slide, but an evolved scale of Q square of 10 to the 4 GeV square, so the LSE scale. You can see that when there's a difference in the central scale we're not including the correlation between the various datasets. When you can see the shift, particularly in the D-valence case, by about like 2% or sometimes even more. So, and also like a change in the distribution in the medium X region. So, the key message of this paper is, if we want to perform an accurate measurement for fundamental parameter like MW, sin squared theta W, or alpha S, we need to take into account correlation and systematic and uncertain correlation in a proper way. In slide number 10, here I would like also to show you the impact of the various data sets in the fit. And the first one I would like to show you is the impact of the inclusive WZ data. So we removed this data, both are 7 ATV. And so this is the fit in the blue, represented by the blue bands. And you can see from the plot on the left-hand side that when removing both the 7 ATV WZ data, the ratio, the strange to the light sequence is very poorly determined. So, what we decided to do is that we retain the precise WZ 7 TV data and remove just the ATV data. This is the plot on the right side here. Comparing the red to the blue, you can see that whereas the WZ 7 TV serve to fix the low XC quark, the ratio here. Anyway, the ATV data still had something in the IX regime, like lowering a bit the uncertainty, but also pulling up this arrest determination a bit. Talking about the uncertainty, here you have the uncertainty for the valence and the gluon, respectively on the left and on the right hand side. You can see that the fit without the 7 TV WZ data can constrain the valence and the gluon PDF, but of course, inputting this data, results in a substantial decrease of the value of the uncertainty. Next data set, the impact in the next data set I would like to talk about is the ATV V plus jet data. And okay, Atlas released like 1 year ago, more or less 1 year ago, a fit using ERA plus WZ data, 7TV plus the B plus J data TV. And I mean, basically this slide is just to tell you that we confirm what we found in the paper. So you can see that adding this, I mean, the ATV WZ data are sensitive in the IX regime, and basically their effect this data is the harden the IX D bar and soften the S bar in the IX regime. Again, having a look at the light, the strange to light C quark ratio, the plot on the left side, this one here, you can see that without this data, we cannot really determine the IRS ratio in the IX regime. And slide number 13 here, I would like to talk about the impact of the TT bar data from the fit. You can see here two plots when we remove both the 8 and 13 TV top data. And you can see that here, the impact of this data is marginally softened the IX gluon for X greater than 0.1. And of course, I mean, reduce the uncertainty of the gluon in the same X region. If you have in mind the results from the ATAS PWZ top 18 fit, where we fit the ERA data plus the WZ data plus the top data TV, I mean, here it seems that the impact of the top data is milder compared to what we previously found in 2018. But I mean, you should also keep in mind that here we have many more ATAS datasets added in the fit. Last but not least, here, slide number 14, I mean, we removed the photon ratio data, and so the plot here on the left-hand side, and this results in a marginal softening of the IX gluon, but no decrease in the uncertainty. While, I mean, when we remove the ATV inclusive J data, I mean, we have a marginal shape change in the shape for the gluon for X greater than 0.01, sorry, but a very substantial decrease in the IX uncertainty as regards the gluon PDF. So, talking about the parameterization uncertainty, I mean, here, what we did for this analysis, I mean, we performed the parameterization uncertainty in the same way as done in the ERA fits. Basically, I mean, we keep adding the degree parameters represented in the equation above till the chi-square doesn't improve by much, so by 1 unity or so. But also, we also consider like adding parameters to have like changes in the shape, even if the chi-square is saturated. So here, I mean, we added 2 extra parameters, basically the FUV and the DDVAR. You can see that adding these parameters produces a model shape change with respect to the uncertainty. Something, this is the first time it's been tried. I mean, we made shades to the Chebyshev polynomial, but I mean, we haven't found any improvement in chi-square, and the PDFs, resulting PDFs were compatible within the uncertainty with the ordinary polynomial fit. Talking about the model uncertainty here, slide number 16, I mean, to evaluate this uncertainty, we vary the input samples for the fit. And you can see here at the bottom the impact of the various model uncertainty on the gluon PDF. You can see also having a look at the chi-square reported in the slide that the largest variation in this model uncertainty is given by the variation of the starting scale Q naught. And this is the orangish line here in the middle plot. And something also I would like to know, if you like, I would like to notice you, if you have a look at this plot on the right-hand side, is that we added as an extra additional uncertainty the difference between 0.6 and 0.4 the jet radius for the inclusive ATV jet data. We choose to fit the R equal to 0.6 data because this choice is theoretically preferred. Then you have the link for the reference here. So we combine the model and parameterization uncertainty I described above with the experimental uncertainty. And here you have like some plots showing you, how the final uncertainty looks like when added in quadrature and combined with experimental uncertainty. And here you have the D valence and the gluon on top, and the D bar and the RS at the bottom. So as you probably remember, I mean, when performing the QCD analysis of the Atlas WZ data at 7 TV, I mean, we found, I mean, the main outcome of the analysis was the unsuppressed strangeness of at low X, which so the RS ratio to be around 1, or even a bit larger, I would say, when if considering it at X equal 0.023 and initial scale was about something, yeah, 1.1, as you can see here. And we would like to, and here I would like to show you that now the RS has come down from 1 as found for the EPWZ PJ 20 case to around 0.8. And something really nice to notice is that as soon as the various global filters like MSHT, CT, and NPDF include the WZ7TV Atlas data, they move from around 0.5, which is represented by the white marker here, to something like very close to what we found here in the Atlas PDF 21 fit. And this is particularly visible at the initial scale and also at the MZ, I mean, at the scale, LSE scale, like Q square equal to MZ square. Finally, I mean, as I told in my introductory slide, I mean, this is the first fit in Atlas where we consider an enhanced tolerance, and I mean, this has been determined using the MHST dynamic tolerance procedure. So after performing a few checks, we decided to go with an enhanced tolerance of equal 0.3. And here you can see for the gluon, the U valence, and the strange PDF, respectively on the left, middle, and right-hand side, how the uncertainty on the Atlas PDF fit looks like compared to the one from CT18A and MSST. As you can see, at low X, we have like a pretty nice agreement with these two global filters, while of course, as regards the uncertainty in the IX regime, and this is particularly visible both for the gluon and the S bar, I mean, the Atlas uncertainty are expected to be larger because, I mean, we don't include fixed target or Tevaton data, which are included in the other global PDF fits. Last but not least, here, I mean, we have some plots showing you the comparison to the various global PDF sets. Here you have U valence and the D valence. I mean, we have like a pretty good agreement between the U valence, but it's something really nice to notice. It's particularly visible here in the bottom left-hand side, that as soon as we add more and more LSE dataset, when our central value moves towards like the global filters, and you can see the difference with respect to our starting value, which is the ERA PDF 2.0 prediction. Slide number 21. Here you have the comparison between our prediction and the U bar on top and D bar at bottom. And here, I mean, I would like to show you that, I mean, also for the D bar, adding LSE data, I mean, make the Atlas PDF prediction like closer to the global filter and in good agreement with CT18A and MSST 20. And I mean, especially here where we have like in the IX region where the D bar is much harder. Slide number 22 here. I mean, they have the comparison for the gluon and the strange. I mean, as regards the gluon, we are more similar to ERA PDF 2.0. But LPDF 2.0, this can be explained by the fact that we don't have so much Atlas dataset in our fit. But last but not least, I also would like to draw your attention on the fact that now, as soon as CT18 and MSHT include the Atlas WZ data, we have like a nice agreement for the S bar distribution over the whole expected X range. And this is basically the end of my talk. So, I mean, the Atlas PDF 21 fit demonstrate that this is possible to fit simultaneously, and also with like a small uncertainty, a very wide portfolio of Atlas dataset for different years. And okay, something, I mean, the key message of this paper is that the making proper usage of the detailed correlated uncertainty as recommended by the experimental collaboration, like Atlas, is essential to beat down uncertainty and achieve precision demanded by experimental uncertainty. So, I mean, using the detailed correlated uncertainty as proposed by our collaboration is very important for any fits, for instance, for alpha S to alpha S, because alpha S is very sensitive to small changes. Something else I would like to say is that the usage of NLO theory is essential. And we still have data available for analysis. And we will have the LHC run tree starting. So this will allow us to push down the experimental uncertainty factor, I would say, and even more of the LHC phase space will be available to reach. So stay tuned, and thanks a lot for listening.
Okay, wonderful. Thank you, Francesco, for this nice presentation. Do we have questions? Yes, Ekaterina.
Hi, Francesco. So I really appreciate your talk. It's a great job which Atlas has done, in particular in understanding all the correlated uncertainties among the data sets. So CMS is not yet there. Fantastic.
Thanks.
I have a question to the strangeness distribution, because you always compare the RS and RS. Maybe it's a matter of taste, but I don't like it that much, because we know it depends on X, and we would like to understand how also it depends at a bit higher X than at the measured values. Do you have some comparison maybe in the backup for the RS with the global PDFs?
Okay.
So you have the standard 4.
No, unfortunately, this is something we are going to add soon to our paper. We have been asked to add the RS distribution. The point is that, okay, we will make this plot, and we will make available this plot for sure, with also the uncertainty on the various PDFs. The point is that we cannot go too much higher in X, because then at some point, like after X equal to 0.4, I would say, some experimental uncertainty on the global fit will go completely crazy.
Yes, right. It explodes. Yes.
Yeah, but this is something for sure we will add in our paper, and as soon as we add it, I can show you the plot.
I'm asking just for personal taste reasons, because in CMS, you probably know, we always plot the RS as a distribution and compare that to the global fitters. And it would be really great to have once a nice comparison Atlas CMS as a distribution.
Sure.
And of course, like the new TEF, they always calculate the kappa. We can also calculate the kappa, but it's also integrated observable. But I think for us who do the PDF fits, it would be just good to have the distribution as a function of it at some scale, maybe not at the starting scale, but at the mass of the W, for example, or both. That would be very good, I think.
Sure.
Thanks.
This is something I don't have in the paper, but we will add it. I don't have here in my slides, but it will be added to the paper. So I will also send you some plots.
Thanks.
Everything is public. Thanks.
Okay, thanks. We have a question here from the room.
Hello. So this is a question that I'm going to ask you, but I guess that I could have asked, virtually any of the speakers this afternoon. So if you look at, the chi-square, per number of data points here, Have you ever computed the p-value corresponding to these numbers? Because it seems to me that it's ridiculously small.
Well,
I'm asking for the p-value. I haven't seen a p-value in the whole afternoon.
Yeah, it's actually not very typical for the PDF fits to give the p-value. I mean, it's not really. But you have so many data sets, you cannot really rely on the p-value anymore. We always have all these questions coming in the collaboration from the statistics expert, but it's not when you. I mean, when you use these huge amounts of data, different data sets, sensitive to different aspects of the PDFs, I think. Maybe my colleagues from the global PDF collaborations can comment on that. But it's p-value, it's not what we.
I mean, that's one of the recommendations for an enhanced delta chi-square tolerance that Mandy mentioned in her talk. Given the fact that yes. So the global PDF fits, we tend to expand that even further. Just because of, well, for example, tensions between data sets or even within data sets don't allow the nominal delta chi-squared equal, and even the p-value, the nominal p-value, I think, to have much sense.
But sorry,
it's not only correlations in the data sets, etc. It's also the theory uncertainties, which are quite large, and this, for example, the missing higher order uncertainties, coming back to this favorite topic, if they are not included, then of course p-values will be ridiculously low.
Yeah, I was just going to say something about this as well. I mean, I agree with both of you that it does illustrate the tensions, and the tensions are sometimes clearly due to failings in the theory. But the tensions are occasionally between data sets that are basically equivalent data sets that are just not consistent with each other. Some of these tensions are between exactly the same type of data in different data sets, and it's just impossible to fit all of them as well as you might both at the same time.
I was not implying that the effects is only from theory. Yeah? So certainly there are also effects in our experimental data. That's right.
Yeah, it's both. It's really both. I agree with that.
But sorry, isn't the aim of this enhanced tolerance criteria exactly to restore somehow a chi-square of 1 such that then one has better defined uncertainties?
Well, it's only applied to the uncertainty procedure, not to the fit quality at the best fit.
The chi-squared you just saw does not include the enhanced tolerance.
Yeah, this is just for the central value. I mean, yeah, Simone, sorry. I mean, maybe this was not clear. I mean, the enhanced tolerance is just enlarging the uncertainty band. It's not actually changing the central value.
Yeah, but I thought these were with PDF uncertainties. It would be interesting then to have the exact same comparison with PDF uncertainties for every PDF.
Okay.
We have our questions to the speaker now.
Yeah,
yes,
I have one question particular to this. So there were a few data sets where you include the scale variation in the fit. And I assume that given your chi-squared or so, you somehow also could produce the pulse and the nuisance parameters, right? So
yes.
did you look into that?
Yeah, and I mean, I can tell you that. I mean, there were. Sorry, I hear a bit of echo. Sorry. Okay. I mean, I can tell you that. Okay, we are. I mean, treating the scale uncertainties as correlated, but also here you have the case where when we included the 7 and 8 TV scale uncertainty, we treat them as uncorrelated. As regards the pools, I mean, I can tell you that they are not. I mean, the scale uncertainty are not really pooled. Neither the one at 7 ATV, but they the effect is basically reducing the tension between the 7 and the ATV the WZ data set.
I think we should add there is some information about that in the paper, but Fra hasn't got it in his talk.
Yeah.
So the nuisance parameters of the pulse are in the paper?
No, it's in terms of the difference in chi-squared, whether you do or don't put in these scale uncertainties.
But I mean, if
but
you
this would be very useful. Also,
Okay.
also for the other nuisances, of course, in general. But okay, yeah, thank you.
Can I ask a provocative question, maybe? What is the interest of Atlas and CMS? Because we both experiments, we publish some, we have dedicated groups doing fits of PDFs. What is the actual interest of us experimental collaborations at the LHC to do the job that global fitters are doing in 4 different teams? What is the advantage? Can somebody comment?
Can I comment?
Sure.
I think only the experimentalists really have the motivation to do something, like try to figure out what are the correlations internally between something like a data set with boson plus jets and a data set which has extracted TT bar through the lepton plus jet channel. The global PDF fitters don't know that, only we know that. And we've done it in context of trying to show what difference it makes within our own PDF fit, but it's information we would hope that everybody would use.
I see, but wouldn't it be just simpler if we provide correlation matrices and then the global fitters use it properly?
Well, actually, the correlation matrices are not the best way to present this sort of data. It's much better to show it in terms of individual systematic errors for every source of systematic error.
Right,
So
and maybe just to add from CMS to what Mandy just said. Indeed, we can go back to the measurement, and if we see the tensions between the systematic uncertainties which we don't understand, we can even go back to re-estimation of this source of the systematic uncertainties, and we have also done it in the past.
Yeah.
So then the question is, do the global fitters use then these advanced uncertainty studies that the experimental collaborations are doing?
In the case of this presentation, this has literally only just come on, to the archive a few weeks ago, 3-4 weeks ago. So we would hope so, yes.
And for the CMS, actually, we had a case in particular, that was a 7 TV jet analysis, which we have reevaluated the systematic correlations, and that is what is used by the global fitters now.
And I'm just speaking as a global fitter, I would say that we eagerly use the information provided by the experiments on what decorrelations they consider to be warranted. And it could be dangerous, right, if there's just speculation as to what decorrelations provide a better chi-squared. But in the case of Atlas, for example, if you have these 2-point correlations, then which can be evil things, I think we can admit that the decorrelation is perhaps more warranted than correlation.
David, concerning these global fits, maybe it's not in all cases necessary for all the points of Mandy and Katrina and Joey that I support. It's maybe not necessary to do a full global PDF fit with all correlated experimental data. But to some extent, we have to do it because otherwise there are so many things that can simply go wrong. If you just put out a measurement with a cross-section and then some other people of your collaboration put out another measurement 2 years later, that everything can go wrong there. So we have to account for our experimental uncertainties and correlations in a better way. And that means we have at least partially to do the same things as the global fitters do.
Understood. Thank you.
Yes, thank you, Klaus.
And maybe I can add to this. I mean, we go more and more towards these global interpretations, right? We have seen some with alpha S here. there are groups trying to do global EFT fits of LHC data, and this issue will come over and over in all of these attempts.
Okay, thank you. So, David, you had some other points you wanted to maybe share again your slides, and shall we pick up the discussion we left there? Or
maybe we can start with this but there were many, yes, I agree, we can start with this, but there were many interesting questions also in the Matterhorn channel. I don't know if Stefan wants to share it, but maybe just to clarify this for Klaus, I'm not proposing just simply moving these points up here. This doesn't make any sense. What I'm proposing is that the global fitters take the total sigma top pair quark cross sections and they include them somehow into the global fit, not just the differential ones. And they do the same with the total fiducial W plus W minus and C, and they include them into the global fits so that this information is not separated. And then for Hera, in principle, they could incorporate those things here also. I'm not just saying moving these points up here. I'm saying that the information, that the observables that are contained here, if they can be incorporated into future new global fits, then we wouldn't need this category. This is my question. I don't know if it's clear.
Of course, I have nothing against including more precise data with the appropriate theory into the global fits. That's perfectly fine. But in this category, there might also come other observables, like let's say CMS has investigated R3/2 jet ratios, and Atlas had R delta phi, or the energy correlations, and these are less sensitive to PDFs.
Oh yes,
but
yes,
with NNLO for 3 jets, they will be promoted to NNLO, let's say in the next 2 years or so. So they will be interesting there too. So there's we had a discussion on these categories, and of course we can again discuss categories and how to do it. There's always something new, and it's nice. But there was a reason behind it. This is what I wanted to explain, right?
Yeah, today there is an obvious reason. I'm saying that ideally some of these observables could be just incorporated here, and then the PDF fitters, they don't need to write papers saying, oh, your alpha S extraction is not correct, you should do it with a global fit. Then my answer to them is, okay, so take the data and put it to your global fit. That's what I'm trying to say. Of course, then final states, QCD final states like R2, R3, and energy correlations and all these things, of course, those are not that, those have nothing to do with PDF, so those belong to a hadron collider category. But maybe some of the things that we have currently here in the future, if the PDF fitters incorporate them, that would be naturally there, and then all these concerns would not appear. That's a solution to these concerns. I don't know if the global fitters can comment.
I mean, I think that maybe it should be kept in mind that that paper was written in the context of the neural net PDF fit, which is not trying to find necessarily the best solution, as, for example, CT18 or MSHT20, do, in the sense of doing a chi-squared minimization. So it would be interesting to try to reproduce that, in the context of, say, what CT18 does or MSHT does.
I don't understand that paper as anything to do with NNPDF specifically. As far as I can see, it does apply to all PDF global fits. It's not an NNPDF procedural effect.
I would like to confirm that, because I think my statement still holds that they are not doing the same sort of best fit, best solution, that we do, and maybe it holds exactly the same, or maybe it's a little bit less pronounced. I just don't know at this point. I mean, that's one of the reasons why we, sort of loosened that restriction on the measurements that we included, in the Global Office of Best Determination for PDG.
Okay, as I understand it, it should apply even more rigorously to our type of fit as to an NNPDF fit.
Tom Creech, in his slides, he presented that some of these results. I was wondering what fraction of these 28 measurements are included right now MMS, whatever it is now called, fit. Tom, can you comment on this?
Sorry, which 28 results are we particularly referring to here?
These 28 inclusive fiducial sigma, W plus, W minus, and C measurements. Are those, can those be incorporated into your global fit? You have some of this data.
I have some particular detail. I checked the CMS 8TVW that there was a question about earlier, and that is absolute data that's included rather than normalized. But to answer for the 28 individual measurements, I have to take some time. So I have to look into them individually and see which ones we have. But there will certainly be a subset included. I don't know if Robert can say any more about this.
No, I mean, we include, I don't know, what is it? Something like about 7 or 8 different data sets, including CMS and Atlas WZ measurements. I mean, we always include them in the most differential form possible. We also always include them as absolute cross sections if it's possible to do so. Some of them are only presented as asymmetries or normalized cross sections. So I'm sure we must have some subset, but again, without looking in real detail, I'm not sure exactly how large a subset that is.
Yeah, indeed. And as I said, given it was asked earlier, the CMS 8TVW would be in an absolute form. But the individual ones, you can send me an email or something, I can let you know when I have a chance to look at them individually.
But I mean, I had a look at the list, and I think most of these measurements are included in all global fits. And actually, if you go back to one slide, I think you had the breakdown. Yeah, exactly here. When you see collider trillion, these are exactly these measurements, right? Either in differential or total, but still, this is kind of exactly the exercise you did in the context of a global PDF fit, right? And similarly, you find here somewhere, I guess, top quark pair production. Here again, probably most of the times this will be differential measurements, but not all of them will be normalized. So I think the global PDF fits are already doing kind of what you say, and maybe there are measurements they do not include for some reason, but then it's just a matter of telling them, there are these 4 additional measurements which are sensitive and you can include.
So what about TT bar, this analysis for TT bar, my analysis of W and C, but also HERA jets? Why don't they? I mean, I guess this is partially covered by this, or?
Well, HERA, I don't know, actually. I would let them answer. I think here it's just the inclusive DIS.
I mean, we have included HERA jets in the past. We didn't on this occasion because I think while we were doing things, the NNLO, well, we need to update to the NNLO calculations in order to do that, which we haven't done so far. So the principal reason why HERA jets are not included.
So after a lot of work, we made these NNLO grids available publicly about, what was it, two months ago or 3, something like that. So it's quite sure that they have not had so much time to use them yet. But then in the future, I hope that the HERA and H1 jets can be included in these fits, of course.
Yes, we've got no, as I said, no in principle reason for not including these data. It's just that we weren't able to include, at the time we did the study, we weren't able to include them at sufficient theoretical accuracy in any feasible manner, which clearly has been improved.
So since this is an exercise for the next 10 years, what would be the recommendation that we make in terms of these subcategories? So top quark cross sections, inclusive cross sections, and W and C inclusive cross sections, and HERA jets. Should those be incorporated into global fits and eventually in 10 years from now removed from here? What is your opinion?
And may I make a comment here? So as far as I remember, this TT bar analysis, that is the alpha S from different TT bar measurements using different PDFs, which are then averaged together. I don't think that it's a good idea to incorporate this particular extraction into something like a global fit, because it's already based on some PDFs.
Irina, I think he means to include the data that go into this analysis to be
right,
included.
but these data are already, but these are in most of the QCD fits. We are talking here about the inclusive TT bar cross sections.
That's my whole question.
These are already in.
Yeah, we include something like about 15 different determinations of the total TT bar cross section in our.
Yeah, and I on the slide in my presentation where I showed the top alpha S dependence, there was actually a plot for the sigma TT bar cross section and how it varies with alpha S, NLO and NLO. So I think they're largely already included.
So then your proposal would be to the PDG to remove those extractions, because this is double counting eventually, not now because those sets do not include this data yet, but in the next set of global fits, these should be removed because those will be incorporated and we should avoid double counting. Is that your proposal? Is this a proposal of this workshop?
Well, I think there will be always the extraction of parameters by the experimental groups, which explore first their data, and then at a later stage it will be used by the global PDF fits.
Yeah,
I think we will never kind of get rid before we have finalized the running at the LHC. I'm not sure that we can get.
It may be too optimistic to think this will happen in the very next round of global PDF fits.
Exactly.
And also, there are some issues in the global PDF fits, like the consistent choice of the many data sets and the consistency between data sets, etc., which is a problem that is available or that is there in the global PDF fits, but which is not there if you just use a few observables. So there are issues that concern the global PDF fits, but not what is in the category with hadron colliders. So at some point one might decide, okay, this value is now overruled by something else and will be removed, but that it will stop to exist in a few years, I have doubts.
I'm playing devil's advocate here, because I mean, I did this proposal. I'm just trying to justify this title, why alpha S cannot be determined from hadronic process, and trying to defend people trying to eliminate this from the. So I'm playing this game here. But I'd like to hear from Daniel also about the Hera jets.
Yeah, just David, I'm not an advocate of Forte and Kasavov in that point. It's not my exact point of view, right? So I'm not subscribing fully to what they are writing, just to make this clear.
Yeah, I have just a few comments on the DIS jet data. First of all, NNPDF, since Juan is not there, the DIS jet data is also included in NNPDF 4.0, and they have seen that they don't have any impact, and therefore they have excluded it again, but they also used the recent grids. So just to add this, that they have used them first in the PDF fit. On this alpha S paper here, what you're discussing here, it's called why alpha S cannot be determined from hadronic processes without simultaneously determining the parton solutions. I would actually like to ask it the other way around. Why cannot PDFs determined be without alpha S? So I mean, if we cannot determine alpha S without the PDFs, then we cannot determine PDFs without the alpha S. But at the same time, now we have all the PDFs determined without a free alpha S. So this is kind of in contradiction. So I don't understand actually the implication on these two correlations. And actually on these kind of combinations, ideally, of course, we want to see an alpha S dependence from any individual data set first. We want to assess first which alpha S sensitivity has a particular process with a particular certain precise calculation and a dedicated measurement. And once we have it assessed for every single measurement, every single process, then we can do a combination, something like the PDF fitters do.
Yeah.
But directly jumping to a global fit, I think this is too fast.
Can I just comment on something? Daniel's made a good point there, but in general, all the codes that any experimentalists use to predict interesting standard model cross sections, the codes themselves use fixed values of alpha S, and you can put in any PDF uncertainty, but it has a fixed value of alpha S. And if you want to know the uncertainty due to that, you have to run it again with a different fixed value. But if you do a PDF fit with free alpha S, then all your eigenvectors get the PDF parameters and the alpha S variation mixed up. So then it's not easy to feed that PDF into a code that you've got that is assuming fixed alpha S. So I think that's why it's not done.
No, that's not quite true. So basically for the H1 PDF, exactly this is done. Then you can basically do kind of linear algebra calculation. And then only two eigenvectors have an alpha S dependence, and all the others have basically the same alpha S dependence.
But my comment was in general about the way the global fits work.
Talk about physics here, not about technical limitations, which can be easily overcome with a few minutes of coding.
Daniel, that's effectively what we do. We produce a set of PDF eigenvector sets, then an extra pair of eigenvectors corresponding to alpha S variation, which CT showed long ago. You can add in quadrature with the PDF uncertainty and produce the correct answer.
Yeah, that's interesting. This makes the assumption that alpha S and PDFs are uncorrelated. This was, I think, first published by CTEC in 2003 or so. And I also see this in my field. So basically, mainly PDFs and alpha S are uncorrelated, and therefore you can treat them separately. And therefore, I don't understand why alpha S cannot be determined without simultaneously determining the PDFs.
It can be. We actually do a fit where we determine alpha S as a free parameter in the fit. So do other groups. We then present our PDFs at 118 because that's what lots of external users want them at. The world average value rather than our preferred value.
And it's the opinion of CT18, well, just for example, that the PDF fits do not have the same sensitivity that goes into the world average. Consistent with the world average, but not with the same uncertainty.
So